Welcome. In this lecture, I'm going to go through a particular comparison property for the integral. I'm not sure that one will always use this, but it starts to give one an idea of having in your mind of kind of how to bound an integral if you don't actually know the value of the integral. And the other thing is that it has kind of nice visualizations that can kind of help you to understand what's going on. So I decided to include this. So here we go. So suppose we have that. So we have that m is going to be less than or equal to, and then we have this function f of x, which is then going to be less than or equal to, and then we have m. So little m and m are just real numbers for each, and this is going to happen for each value of x that lies between, we have some fixed a and b. So for each a less than or equal to x less than or equal to b, meaning each of these x's that lies between a and b. Okay, now let's look at this picture of what occurs. Okay, so this picture is going to be for when we have that f of x is greater than or equal to 0, again, for each a less than or equal to x less than or equal to b. Okay, so for each x that's in that interval, this function is always greater than or equal to 0. Okay, and then here's the picture, which is that I'm going to have, I'm going to draw my, like this. So this is the y-axis, and this is the x-axis. This is y and x. And then I have some kind of function like this. So it's going to be going maybe up and down. Maybe I need to go a little bit slower for it to actually show up. It goes up and down a little bit. But it's always staying right above the x-axis. That was kind of the key point here. Okay, and this is my, this is the graph of my function, so this is y equals f of x. And then this is going to be between, so on the bottom we have, so it's always above here. So it's always going to be above y equals little m. Okay, and it's always below y equals big M. Well, what do we know about these areas? So, and then I have these, right, I have this A and B, which are here. So we have x equals A, and maybe here x equals b. And then I can look at the areas below these curves. So I have here this area, right? So this area here is equal to, so this area, right? The area under here is going to be equal to, you know, we can just do width times height. So our height is going to be little m, right? And our width is going to be b minus a. Okay, and then for this one here, if I want to look at the area under here, so I want to look at this whole area, right? This is going to be, so this area is going to equal, well, now I'm taking the integral from a to b of f of x dx. And then for this largest one, so it's, again, you can go like this. So this area, that area in there, well, again, I can do my height times my width. So I can do, so this area is going to equal m times b minus a. Okay? So that's this area, which is this integral, sits between these. Okay, and then the kind of exciting part is that this picture is going to hold even when f is not always non-negative. So this picture holds even when this function f is not always non-negative. Right, when it sometimes has negative values, okay? Or maybe even always does. It doesn't matter. So this is the theorem. So the theorem is going to say that, okay, if we're in this setup where we have that always little m is less than or equal to our f of x, which is less than or equal to our big M, right? So this happens on that interval, just like we have over there. Okay, so this happens for each a less than or equal to x, less than or equal to b. Okay, so if that holds that, you know, this function is sitting between these two values within that interval, okay? Let's make sure that this is clear. This is an a, that it's not a 0, it's an a. Okay, then we know that, so if we're in that circumstance, then we're actually going to have that this exact same thing holds, where I have m times b minus a is less than or equal to this integral, and I'm going to go from this a to this b of, and then this function, f of x dx, which is then less than or equal to, and then I have big M of b minus a. Okay? So it's still bounded just like that. So this is the theorem. And let's go ahead and show an example of its use. Okay, so here's an example. So I know that always we have that minus 1 is less than or equal to sine of x, which is less than or equal to 1. Right, so sine of x always stays between minus 1 and 1. Well, it's always true. But in particular, it's true on this interval. If I wanted to look at the interval, minus pi over 2 to pi. Why not? Okay. Well, what does that tell me then? That tells me that, so if I take this minus 1, right, from here, and I multiply it by the width of that interval, so this is pi minus pi over 2, so that pi minus pi over 2 is going to be less than or equal to the integral from minus pi over 2 to pi, right? So the integral on this interval, okay, of, and then I have sine of x dx is then less than or equal to 1. And then again times the width of that interval. So that's pi minus pi over 2. So pi minus pi over 2. Okay, and then we have, so then we can just kind of compute that, and we can get that minus 3 pi over 2 is going to be less than or equal to the integral from minus pi over 2 to pi of sine of x dx. Which is then again going to be less than or equal to 3 pi over 2. Okay, so let's just kind of go through what we were doing here. This is a very nice, this is a nice way to kind of bound your integral, like to know what your integral has to be between, and sometimes it's actually enough. Sometimes that's all you need to know about your integral. And really, seems complicated to remember, but actually if you always just remember this picture here and remember that it works even if your f is not staying above the x-axis, right? Then you're good to go, because it's just saying that this area is less than or equal to this area, which is less than or equal to the big area. Okay, so I hope that made some sense, and I'll see you in the next lecture.